Here I've built a full adder, and I'm going to explain how it works. So it's a full adder because it adds three 1-bit binary numbers. Two of them are just the inputs, and one is a carry in. So you can carry in from anywhere you want. The AND gates and the OR gates here work to compute the carry out. And so what they're basically doing is detecting if there's at least two high inputs from any of these inputs. If there's at least two ones, so here's two, then it'll carry out a one, even with three. But just one will not produce the carry out. And then the three exclusive OR detects if there are an odd number of high value inputs. Because if there is a high number, then the sum will always have a 1. So if there's just 1, there will be 1. 2 will produce 0, because 1 plus 1 is 0 with a carry out of 1. But 3 will be 1 with a carry out of 1. And that's the full adder. Here I built a 4-bit subtractor. So I went with the version with the negator and just adding it on to the bits because that made more sense to me. So we take our 4-bit number first. Well, if I want to do, say, 5 minus 3, I'm going to enter my minuend up here, 5, and we're going to add on to that the 2's complement of our subtrahend. So 5 minus 3, so I'll put 3 in. So 3 goes through the 2 negator here, where it is complemented and then incremented. One's complement first and then an increment. And then that value, those values go into our second adder here. So the 2's complemented 3, which is negative 3, is now added to 5. Now it comes 2 with a carry bit of 1. I'm going to explain how this multiplier, that's probably a better word, how it's designed and why it's designed in this way as a logic circuit. So first of all, we have our two operands. I think that's what they're called, B and A. So B is being represented by this hexadecimal keyboard over here, and it's being fed into all these AND gates. And A, for simplicity's sake, is just put on each one, the label, but we could also kind of represent that with a hexadecimal. It would just have to be plugged into each one. So basically the multiplier is made of kind of two cascading operations. The multiplying, which is done by these AND gates, and then adding. And the reason we have adding, in addition to the multiplying, is just how longhand multiplication works. So say we have A and it's 1, 0, 1, 1. B is whatever, 0, 0, 1, 1. And we're multiplying them. Well, the first thing we're going to do is we're going to take the first term on the bottom here, and we're going to multiply it by each term on the top. So we would have 1, 1, 0, 1. And so that's done in this step right here. And AND gates actually just function as simple little multipliers. If you have a 0 and a 1 going into an AND gate, it's going to produce 0. And 0 times anything is 0, so that's correct. 0 times 0. 0 and 0 will be 0. But only if you have 1 and 1 will it produce a 1. So it's basically just does a simple multiplication. But the reason we need adders is because you're going to move on to this next step where you're going to take the second term in B, which is 1, and also multiply it by 1, 1, 0, 1. And if we go on by each term, the next two terms are zeros, so it's just going to be 0, 0, 0. And we're moving over each time. And then we add all these terms together when we're doing longhand multiplication, as well as drop these terms on the side. So you can see there's 3 terms that drop there, the 1, and the 0. And if you look over here, that's where we have this A0 and B0. That's dropping down to the bottom. We have a second one dropping down, and a third one dropping down. That's those terms, because they're not being added. Well, they are being added with some things, but. So then when we add things, when we have these adders, we're adding all the terms from kind of the second stage right here. Adding all those terms. So it's the same as these ones right here. We're adding them against 3 of these first terms. Since we already dropped this one here, these 3 are getting added against the second, just like over on our longhand multiplication. So we would drop the 1, we'd add these 1s, that'd be 1, 1. And then we have this carry out bit here, which is going to be added on, and that's represented here. That's what we feed in as our 4th term. On the first step, there isn't one, it's always going to be ground. It's always going to be 0. So we have ground there. And then we have the carry out bit fed into here since we're losing the first bit, or at least the least significant bit. We're not exactly losing it, but for each level that cascades down, the least significant bit is dropping down just straight into the product instead of carrying over. So here we have the inequality logic circuit, and I'm going to explain how it works and why it works that way, why it's designed in that way. So first of all, we have 3 possible outcomes. We have A is less than B, A is greater than B, and A equals B. So I'm going to start over here to explain just this little section, because basically the whole circuit is these sections just for each bit. And we have 3-bit numbers here, 2 3-bit numbers, A and then B. So we start on the greatest or most significant bit, and for the starting at these AND gates here, right here, each of these is detecting whether A is bigger than B or B is bigger than A. So this one is trying to find if B is bigger than A, and this one is trying to find if A is bigger than B. And the way they do that is, if it's detecting, for this top one, it's trying to detect if B is bigger than A. It has to do them separately. For the top one, it's going to feed B just right into the AND gate, and it's going to complement A. So if A is 0 and B is 1, well, obviously B is bigger than A, so we want this gate to output a 1. So 0 is going to be complemented, and we're going to have 1 and 1 going in. So that's perfect. That'll produce a 1. And that 1 will go all the way along here and just go straight into this OR gate, and we'll immediately get a high output for A is less than B. Because we know that if the most significant bit is bigger than the other number's most significant bit, we don't really even need to worry about the other bits, because we know that the number with the biggest significant bit is going to be bigger. And then for this AND gate, it's basically the same. It's just trying to find if A is bigger than B. So A is going to be fed directly in, and B is going to be complemented. And the logic will basically work the same. If A is 1, B is 0, B will be complemented into 1, so it'll be 1, 1, and this AND gate will put out a 1. However, if both of these have, say, as 1, well then A is complemented for this top AND. It's going to be 0 and 1, so that AND gate isn't going to output a high value, and neither is the bottom. Instead, what we're going to get is this will put out a 0, and this will put out a 0, both AND gates. So then this NOR value, this NOR gate will output a 1. It's getting both of those. And this NOR gate, as well as the other ones on each little level here, those are basically trying to find out if they're equal. So if A and B, the bits for A and B are 0, 0 or 1, 1, then this NOR gate will output a 1 to find that they're equal. But different from the AND gates, this doesn't feed right into one of our final output gates here. Instead, it feeds into another AND gate. Because if the most significant bit here is equal, well then it just has to go to the next significant bit and has to find out if those are equal. If one of those is bigger, then that number is bigger. But if not, if this NOR gate also outputs a 1, so it's equal, then it'll just go on to the next level and check if this one's equal. And if they're all equal, then that'll all feed into this bottom AND gate right here, and that'll output a 1, and we'll get A equals B. And that's the basic functions of it and why it works.